introduce our distinguished speaker for today's section, Dr. Bindu Krishnan. She is a doctorate holder in statistics with over 20 years of experience in academics, research, and industry. Currently, she is working as senior data scientist in Data and AI at IBM Research and Development Software Labs Kochi. Dr. Bindu has served in reputed institutions including Jain University, Kochi as a professor and head of data science. She has also authored a book and published several research articles in the leading international journals. With a deep expertise in data science, artificial intelligence, and machine learning, she has delivered many invited talks and hands-on sessions across India. Today, she will be speaking on the topic recent trends in AI and ML techniques in global perspective. We are honored to have her with us and I warmly welcome Dr. Bindu Krishna to lead this section.
Thank you. Good evening, all. First of all, let me express my sincere gratitude to the organizers, principal and management, KMEA College, for this opportunity. Of course, as in the introductory session, in the inaugural speech, sir mentioned just like that. Of course, this is an emerging area. Actually, that word is not enough to explain this particular thing. And of course, I congratulate the team for choosing such a wonderful team for this particular session. Okay, straight away, I'm moving to the session. Okay, so hey, from the industry, I would like to share something specially on this particular field from the industry perspective. So we know this high performance technologies have become increasingly important in recent years. So along with global computing, of course, including Internet of Things, this artificial intelligence jobs, I can start with the opportunities. AI jobs are booming. Or specifically, I can say machine learning job market is extremely healthy and shows no sign of slowing down. So anyway, artificial intelligence is quickly being utilized in business as well as societal functions, creating unprecedented opportunities across sectors and transforming our lives. No doubt in that. And machine learning scientists and AI researchers are actually making all kinds of decisions on how we learn, work, move, consume, and interact with each other. Of course, a quick look at the technology landscape shows the power of this AI in everyday life. From voice assistants that power smart speakers to high-tech coffee makers, these technologies are quickly becoming mainstays of life. And this evolution has led to a positive change in AI and machine learning job trends. Now, in addressing, say, complex societal challenges, AI can enhance decision-making process by analyzing a vast amount of data, identifying patterns, and providing actionable insights. By incorporating AI into, say, sustainable initiatives, this AI may benefit a wide range of sectors of economy, including healthcare, energy, transportation, urban planning, and so on. AI might, for instance, help creditors, investors, business makers, and so on, can make optimal decisions for long-term financial sustainability. In sustainable finance, or AI-driven tools and predictive analytics can improve disease detection or protocols, patient outcomes, etc., in healthcare. Or it allows patients to access information, then receive emergency care, then manage their health, then detect diseases, schedule appointments more efficiently, and so on. So the use of AI-driven optimization algorithms, even in energy sector, can also promote the integration of renewable energy sources, then enhance grid stability and mitigate carbon emissions, so thereby contributing to the mitigation of climate change. AI can also contribute by promoting equity and social inclusion, by addressing systematic barriers and disparities that hamper progress towards sustainable development goals. So with the help of AI-driven technologies, even policymakers can improve access to education, healthcare, financial services, and some other essential resources. So while these developments may seem inevitable, experts' hard work in the field of AI and engineering, I can say in engineering, is driving the growth. Of course, there are a couple of core ideas that are frequently used while addressing AI. One of them is our machine learning itself. Machine learning, of course, it's a way we all are familiar with this particular term, machine learning. It's a way to achieve knowledge-based AI through its ability to learn without being explicitly programmed. Or deep learning, take the case of deep learning. It's another approach to ML that suggests learning using neural networks and adapting them to have a layered structure that resembles the cognitive aspects of the human brain. Even another term is big data, which are substantial data set. Although at first they seem difficult, knowing these terms, of course, it's important to understand the overall aim and function of AI. So machine learning concepts, specifically saying machine learning concepts like, say, computer vision. Take the case of computer vision. Quickly open doors to some of today's most exciting even opportunities for forward-thinking technology professionals. So computer vision is just one of the many new AI innovations that's driving current machine learning job trends, or not only job trends, that emerging area. So to better contribute in this particular area, it's essential for us to understand how AI and ML technologies work, and how inspiring or how aspiring AI and ML researchers can learn the skills that they need to contribute those promising innovations in this field. Okay, so anyway, let me share the screen. Is the screen visible? Is the screen visible?
Yes, ma'am.
Okay, thank you. Yeah. So let me start with technically, I'm moving technically. So let me start with, say, one word on these terms, or how these three terms are related. Since this is the first session, I think it's better to start from the fundamentals. Just one word on these three things. Data science. I'm thinking of to begin with the data science. So data. So I can say that that term is the heart or bedrock of everything. Data stands at the heart of today's business, yet maintaining its quality often proves challenging. Or data science starts with data that can range from a simple array of a few numeric observations to a complex metrics, millions of observations with thousands or lakhs of variables. Even in statistics, we can say model. A model is a representation of a relationship between variables in a data set. It describes how or more, statistically speaking. So it describes how one or more variables in the data are related to another variables. Or modeling, simply modeling, just ignore the word statistical modeling. Simply modeling It's a process in which a representative abstraction is built from the observed data set. So for example, simple example, real life example, on a credit based on credit score, income level, and say requested loan amount, a model can be developed to determine the interest rate of a loan. For this task, of course, previously non-observational data, including credit score, income level, loan amount, and interest rate are needed. So data, I think no more explanation is required for this particular term. Data science deals with data, how this particular thing is related to data. Now moving on to the second term, AI, artificial intelligence. It's a wide range or wide-ranging field of study. We all know that is concerned with building smart machines capable of performing tasks that typically require human intelligence. And AI makes it possible for devices, computers or printers, whatever be the device, to learn from experience and perform human-like tasks. But the role of this ML, machine learning, is to observe large amounts of data and make predictions using algorithms, preferably statistical algorithms, ideally going on to perform tasks beyond which they are explicitly programmed. So the distinction between AI and ML is actually crucial, with AI focusing on creating systems that perform tasks requires human intelligence, but this ML is a subset of AI. Sometimes it's a subset of AI that enables devices or computers to learn from data. Both fields offer promising contributions towards the research or towards the opportunities and so on, reflecting a rapid growing job market, even I can say. One side, if we focus on job trends, of course, I know faculty here, not a student group. But anyway, we can't skip this, especially the job opportunities, or because AI and machine learning have grown significantly with these particular things, especially this ML actually cited as the second most sought even after this AI jobs. So anyway, so these three terms actually, AI, data science, and of course, deep learning is a subset of AI. So these three terms, AI, machine learning, and data science, are closely interconnected fields that work together to analyze and make sense of large amounts of data. AI, ML, and data science are all related, but they have different purpose or different purposes and different methods of operation. Data science on one side refers to the field of study that deals with managing large amounts of data through modern tools and techniques to discover hidden patterns, then extract meaningful insights, and make informed decisions, business decisions, especially in industry. So all the process involving gathering, then organizing and examining data are connected to the field of data science. And this interdisciplinary approach actually emerges various fields of computer science, scientific process, methods, and statistics in order to extract data in an automated ways. Or I can say data science professionals utilize mathematical or machine learning techniques. That is the thing. These data science professionals actually uses not only mathematical or statistical things, uses machine learning techniques to handle a vast amount of data effectively. And again, in machine learning, this statistical methods are used to empower machines to learn without being explicitly programmed. Or this field actually focus on letting algorithms learn from the provided data, collect insights, and make predictions on unanalyzed data based on the gathered information. Then AI, artificial intelligence. Of course, that refers to the process of making machines to think without any human intervention. Then weak AI. even we say types regarding the types of a weak AI. Take the case of weak AI. Performs only specific tasks like Apple, Siri, then Google Assistants, Amazon's Alexa, etc. And the second type, general AI, that actually revolves around the idea that a system can manage activities such as speaking, translating, identifying sounds and objects, and executing businesses or social transactions. So general AI actually mirrors human intelligence, making it capable of performing any task a person can. Then again, another type of AI is strong AI. That refers to the building machines that are indistinguishable from the human mind. So I just want to say the difference between these terms, AI, ML, data science. So simply, data science is an interdisciplinary field that brings together abilities from different fields like machine learning, statistics, visualization, and so on. And it enables us to draw valuable insights from large volumes of data, then supporting well-founded decision-making process in the area of technology, scientific research, business, and so on. But machine learning is subset of data science and AI. Okay, subset of data science and AI that utilizes algorithms and statistical models to process data. And this enables machines to learn and make predictions without explicitly programming. And finally, this AI, artificial intelligence, it's a broader concept. Focuses on creating machines capable of performing tasks that require human intelligence. Again, including reasoning, learning, and problem solving. Or I can say data. So from these words, we can say data science actually serves as the foundation for machine learning and AI by supplying the necessary data for these models to learn from. It integrates algorithms from machine learning and borrows ideas from traditional domain expertise, statistics, mathematics, etc. to develop solutions. Okay, so that role of A is different. A actually serves us as a valuable resource for data science in generating data insights, not data insights. The primary distinction actually lies in data science comprehensive approach to data collection, preparation, and analysis, transcending solely algorithmic or statistical facets. Consequently, while machine learning and AI specialists concentrate on algorithm development throughout the say project's duration, data scientists usually must demonstrate adaptability by shifting between various data-focused roles. Of course, as per the project's requirements. So the connection between these three things, that is the first thing which we need to learn or which we need to know. Yeah. Okay. Now, while talking on this particular term, machine learning, of course, we know a lot of definitions on this machine learning. I'm not going purely technical thing towards the machine learning thing, but especially while looking into this particular thing, this particular term, machine learning, or while learning this machine learning, we are not in a position to skip some terms, especially the term predictive analytics. So why I'm mentioning that word here? The reason is that previously I had mentioned only about the term data science. One more emerging term there, data analytics. So that term is analytics again, somewhat that definition is almost similar to data science and data analytics. Analytics again, it's a making use of data for better decision making, of course. But usually there are four, basically, or traditionally I can say there are four stages of analytics. Descriptive analytics, then descriptive analytics, then diagnostic analytics, predictive analytics, prescriptive analytics, where simply descriptive means if we are provided with a data set, just we usually begin with some analysis. That is what happened to that data. Finding, say, we can begin with mean, median, mode, or histogram, or whatever be the things. So what happened to that data? Okay, either through visualization or descriptive measures. Second stage is actually diagnostics. So where actually we diagnose why I'm getting the value like this, or we are actually diagnosing the reason behind different results, I can say, output obtained from the initial stage. Sometimes we skip that stage. Anyway, third stage, I would like to actually concentrate on this particular stage. Third stage, this is closely connected to our machine learning. Because we all are, especially CS participants, all are aware of the terms. Say, begin with linear regression, logistic regression, then support vector machine, decision tree, etc., etc., etc. All these things actually comes under this particular term. So that is actually exact relationship between the term data analytics and predictive analytics. So predictions, we are actually using the predictions here, either in business or industry or academics or any organizations. This part remains same. Now, fourth part is actually, it is closely connected to this remaining three. Of course, we are making some predictions in this stage, in this third stage. So based on that predictions, or it recommends fourth stage, prescriptive analytics actually recommends an action based on forecasting or based on these predictions. So that might not be seen, especially in students' projects or usually academic projects. But this part is very, very, very important in industry, prescriptive. We have to recommend, actually that is the role of even I can say those who are dealing with data, either machine learning engineer or data scientist or AI engineer or whoever be that. The role of that particular person recommends an action based on forecasting. What should I do? For the third stage, actually, we are predicting something. What should I do with these predictions? That stage, actually, we call it as prescriptive analytics. So anyway, so here why I mentioned the reason is that this predictive analytics, actually, all the techniques, whatever techniques which we are using in this machine learning predictions, all those things actually belongs to this particular stage, third stage of data analytics. Yeah, simply that steps that we start with defining project, then collection of data analysis, statistical modeling or some models, after modeling, deployment. Prescriptive analytics. Okay. Now, just I would like to share, especially while dealing with the machine learning projects or AI projects or data science projects, the basic difference between academic and industry. Lot of things are there. I can say the largest skill gap is related to the practical application of this particular area, either theory of AI or theory of data science. In corporate world, data scientists or whoever handling that data, they cannot just focus on simply building the most accurate model or the best prediction. They must also consider the impact on the business. That is the first point, primary thing. Second thing is, business is faster paced, less structured, and more hands-on than academia. So at work, a more pragmatic approach is needed, in which one need to understand the trade-off between complexity and impact. Or one should not be afraid to take, I'm sharing the case in industry, one should not be afraid to take a more iterative approach, pushing one version at a time, rather than waiting until all the research is done before before, say, presenting findings or making crucial decisions. That is one of the major difference. In academics, what we do is that is a usual case, because I am also a person previously in academics. We usually focus, especially because our primary goal is to publish an article in a reputed SCI or similar journals. So we usually focus on obtaining the best accurate model, or a model with the best predictions. But industry case, it is not like that. There actually we are doing stage by stage. One simple case I can say, case of outlier. So especially those who are, I know many participants are there, especially from computer science background. They had done many machine learning or data science projects. So one of the thing which we are doing, say, case of outlier, especially that is one of the thing which we are dealing in during the deep data pre-processing. So what we do is that we will detect the outliers by some methods. Simplest method is box plot. So we will remove the outlier. By box plot, we will detect this outlier and we will remove the outlier. We will proceed there. It is not the case in industry. In industry research, sometimes this outlier itself is the most interesting or interesting part worth researching. Because mainly industry research, actually, it's mostly product oriented. So anyway, another distinction between industry research and academy is the ground data. Although I believe this is changing, but the current scenario is that industry data set tends to have more hiccups, or then again bugs. Then another thing is outliers. I already mentioned. So when analyzing or building models in industry, definitely one needs to be practical and develop techniques to deal with inconsistencies and the data that isn't clean. So that is why I mentioned sometimes that outlier itself will be the most interesting research part. Okay, so these are only some points I mentioned. Usually the goal industry, of course, making money, no doubt in that. But in academia, of course, improve our human knowledge. Then success criteria, publish papers. But in industry, it's not corporate. It's not like that. Create but of course, in corporate also, nowadays, people actually focus on specifically to come up with the patents, not that much interested in publishing papers, because we know that will take a long time. Because publishing patents means that advancements would be like that. But then in academia, of course, approach is to find a better way to do anything, but industry, especially fastest way to do. And importance of speed, very, very important. I'm not saying that it's not that much important, but anyway, we have, especially those who joined for research, even they have time, at least 2 years. Okay, anyway, maybe some people may not join with this last point. Okay. I just mentioned in general, that's all. Yeah, technical skills, we know for this particular area in the introductory talk, I already shared these things. Okay. Yeah, the role of mathematics, statistics, that also I had mentioned. Yeah, another thing. Challenges in AI. What all challenges? Lot of things are there. Even though we say this expanding AI and ML job market, or AI market actually, or AI market or ML market, it offers a wide range of career opportunities, then a wide range of research contributions, etc., etc., etc. But lot of challenges are there for this particular thing. While AI offers, one side AI offers countless opportunities or countless contributions, but it also comes with challenges. I can begin with availability of data itself, because we always begin with data. AI is only made possible with the availability of massive volumes of data and sources of data. Currently, many industries and business processes are still paper-based and struggle with digitizing their data. Even take the case of medical clinics. That itself is one prime example of such industry. Especially if we visit, say, some villages or some rural areas, we can see still paper-based, whereby patient records and appointment scheduling are done manually. Even for organizations that have digital information, some organizations, they are actually significantly limited by the access to and quality of the data. That data are stored, even the data are stored in silos with very few integration points. And the quality is, I can say, it's often inconsistent and in a variety of format. So that it's one of major challenge, availability of data. Even some researchers are in this group itself, some researchers are facing, because many organizations or in healthcare or whatever be the field, they are not willing to share their data. One part is confidentiality, of course, but the other side, actually it is not readily available. That case also is there. Lot of organizations we can see. So that itself is the initial challenge, I can say. Then second, data quality. Second point. Even though I have mentioned a lot of points here, let me say 3 or 4 important points that belongs to these challenges. Take the second case, data quality. Ensure the data is right, complete, and relevant. That is very, very important. Second point. Now, third one, ethical consideration. Handling sensitive data responsibly and addressing ethical concerns. Ethical consideration, that is very, very, very important. Actually, that is one of the reasons organizations are not willing to share their data. People will handle it careless. That's the only reason. So that is one of the challenges. One among the challenges. Then again, a lot of things are there. Say, take the case of public trust and responsibility. No matter how AI becomes, how advanced AI becomes, if people don't have confidence that AI applications are trustworthy and are being implemented responsibly, then technology is not going to have a wide option. So public trust and responsibility, that is very important. Again, another thing, say, interdisciplinary collaboration. Bridging the gap between, say, that experts, either data scientist or data analyst or machine learning engineer, whoever be that person handling data. So bridging the gap between that person, then domain experts and decision makers. Sometimes, say, take the case of a data scientist. Background is, assume that his or her background is BTech computer science. If he is handling a data in finance, so there itself we can see the lack of that domain expertise. He's not expert in finance, or if his role or responsibility is to handle some economics data or some data from some other fields. So that then finally how to make decisions, again challenge. So interdisciplinary collaboration, that is bridging the gap between this data handling person, domain experts, and decision makers. That is one of the challenge. Again, lot of things are there. Another thing, an important thing is algorithmic black box. So another challenge. In this, another challenge I can say it's an important thing. Ability to understand how AI reaches its conclusion, or to know the reasons behind how the machine arrives at a particular decision. So that lack of transparency and potential bias that could go undetected, we can say it's an algorithmic black box. So anyway, similar to this, lot of challenges are there. Now, again, if we talk on, just leave those challenges. Sorry. If we talk on the impact on AI on various sectors, say begin with healthcare. It's like in healthcare, of course, AI improves patient care by analyzing data to personalize treatments, predict disease risk, and perfect hospital operations, enhancing overall medical outcomes. Or in healthcare, I can say AI is like a smart assistant for doctors, making healthcare more precise and efficient. So here, just I can say, okay, the case of IBM. IBM actually we have Watson. Some of the people might have learned about, heard about that. IBM Watson Health employs AI to enhance healthcare by providing personalized diagnostic and treatment recommendations. So this particular Watson's natural language processing capabilities actually enable it to sift through vast medical literature and patient records to assist doctors in making more informed decisions. It's not a campaign, just I'm sharing, that's all. Okay. Or again, I can say Path A. Another thing is just leave that IBM. Path AI. Path AI actually utilizes AI algorithms or techniques to assist pathologists in diagnosing diseases more accurately. How is it possible? So actually, by analyzing digitized pathology images, this Path AI system can identify patterns. Patterns and anomalies. Of course, patterns and anomalies that the human eye might miss. And that this analysis actually speeds up the diagnostic process and of course enhance the precision of pathology reports by even I can say more than 10%, leading to better patient care. So I just specified two examples. One is IBM's healthcare and Watson healthcare, and another thing Path AI. So similar to a lot of things are there, a lot of products are there by different organizations. So keep in mind, all these things are actually one side, we can say impact of AI over this in healthcare. Okay. Now take the case of finance. In finance, AI is like a financial wizard using data to manage the risk, detect fraud, and make smarter investment decisions. Or in finance, this AI is actually simply saying about turning numbers into insights that shape the future of banking and other financial strategies. Again, retail. AI boosts customer experiences by analyzing shopping patterns, recommending products, and perfecting inventory, leading to personalized and efficient shopping journeys. Or this AI in retail, actually AI help businesses to understand customer preferences or reduce cost and create a tailored shopping environment. Again, take the case of education. In education, AI helps personalize learning by analyzing student performance, predicting needs, and perfecting teaching methods for individualized educational experiences. Or simply saying, AI empowers educators with insights to enhance student outcomes and adapt new educational technologies. So if we take any, whatever be the field, we can find this impact of AI over that sector. Simply, I have included only these 4 areas. So whatever be the area which you are choosing, of course, we can find something like this. Yeah. So anyway, this particular AI actually, it impacts many aspects of our lives. It's commonly used in interactive systems to provide personalized services in the form of virtual assistants like chatbots or something. Then smart homes, fraud detection, clinical decision making, particularly in medical imaging. Then adaptive learning system, and many other platforms in just about every aspects of our lives. So as more AI applications continue to develop and deploy, the social implications of this technology is paramount. Or it's time for us to engage the general public in understanding how the technology works and to prepare future generation to live with and use AI based on their particular or interest, based on their interest, best interest. Okay, so now moving to, let me specifically say some case studies in some particular area. So here simply I by random choice I have included say healthcare diagnostic, and because now healthcare actually that is one of the I can say common or important or popular one that we focus on nowadays, especially while talking on this AI. So that's why I have included the first one itself as healthcare diagnostics and treatment personalization, then predictive maintenance in manufacturing, then fraud detection and prevention in finance, then e-commerce personalization and recommendation systems, then agricultural yield prediction. A lot of things are there. It's only I have included only a few here. Yeah, I have already mentioned about this IBM Watson X. So it actually demonstrated. Just say a few words on each of this. Not only I'm a person from IBM, that is why I have taken this. I am not saying that this IBM Watson is the only AI tool in this particular. No, lots and lots of AI tools are there. Since I am a person from here, that's why just I'm taking only this IBM tool. So this actually, it has demonstrated over not 15%, now actually more than 30% increase in the accuracy of cancer diseases when assisting oncologists in analyzing complex medical data, including genomic information and medical journals. Or in general, I can say, even lot of things, IBM's health AI-powered recommendation, it helps reduce the average time it takes to develop a personalized cancer treatment plan from weeks to just a few days, potentially improving patient outcomes and survival rates. Then Watson's data-driven insights contributed to 30% reduction in medication errors in some healthcare facilities by flagging potential drug interactions and allergies. Then again, it has processed over 200 million pages of medical literature to date, providing doctors with access to knowledge base that can inform them. So anyway, this particular thing actually, IBM Watson Health actually employs AI to enhance healthcare by providing personalized diagnostic and treatment recommendations. Especially here, actually, we are using natural language processing. Watson's actually natural language processing capability, NLP, our NLP, CS, computer science, CS people's NLP. So Watson's natural language processing capabilities actually enable it to sift through vast medical literature and patient records to assist doctors in making more informed decisions. Now, moving to path. That is again belongs to this particular field, healthcare. Path AI's different pathology platform that has shown a 25% improvement in diagnostic accuracy compared to traditional manual evaluations, especially while identifying challenges cases like cancer subtypes or rare diseases. Then again, in a study, actually, they help pathologists reduce the time it takes to analyze and report findings by 50%. Then by using the machine learning techniques, actually, they are able to significantly decrease the rate of false negative and false positive in pathology reports. Then again, PATH's platform actually processed millions of pathology images. So that is why I mentioned previously, actually, PATH-AI, they are mainly utilizes machine learning algorithms. For what? To assist pathologists in diagnosing diseases more accurately. So that procedure is that simply by analyzing digitized pathology images, PATH's system can identify patterns and anomalies that the human eye may miss. So that analysis actually speeds up the diagnostic process and thereby enhances the precision of pathology reports by more than, of course, 10%. Leads to better patient care. Okay. Another, Siemens. I think, yeah, so, Madam, 7:30, we need to give a break, right?
Actually, ma'am, it's like 6:30 to 8 is the first session we are planning.
Okay.
8 to 9:30.
Oh, 8
It's
o'clock.
okay. It's up to you. No issue.
No. I thought it's 7:30. No. Okay, 8. I'm happy for that. Okay. Just I'm actually trying to ask your permission. Can I finish this and then give break?
Yeah, sure. No issue.
Okay. So let me finish this case studies and I'll give a break. Okay. So, yeah, thank you, sir. Thanks. Yeah. So, yeah, next is actually Siemens. We all are familiar with this Siemens. Predictive maintenance in manufacturing. Okay. So this Siemens has reported actually a remarkable more than 20% reduction in unplanned downtime across its manufacturing facility globally while implementing this predictive maintenance solutions. Again, they achieved a 15% increase in overall equipment effectiveness, resulting in improved production efficiency and reduced production cost. Then a $25 million annual cost savings in maintenance procedures directly attributed to their data science based, and of course, machine learning itself. So, of course, we know that the Siemens, it's a industrial giant, no doubt in that. Siemens embraces predictive maintenance through AI. In one word, we can say. Again, they are using machine learning algorithms mainly to monitor and analyze data from their manufacturing machines. Next one, PayPal. Everyone is familiar with that, a leader in online payment. Okay. So PayPal's real-time fraud detection actually reported even 99.9% accuracy in identifying and blocking these fraudulent transactions by minimizing the financial losses for company and users. Again, they reported proactive fraud prevention measures. Of course, that saved users an estimated $2 billion in potential losses due to unauthorized transactions in a single year. Then, the average time a PayPal's data acquisition algorithms to detect and respond to a fraudulent transaction is just milliseconds. Ensures that fraudulent activities are halted before they can happen. So, PayPal's continuous monitoring and data-driven approach to fraud prevention have resulted in a 40% reduction in overall fraud rate. So anyway, in summary, I can say PayPal employs advanced AI techniques to detect and prevent fraudulent transactions in real time. They actually analyze transaction data, user behavior, and other relevant factors to identify suspicious activity. Okay. Now, Amazon. Everybody is familiar with this, Amazon. The e-commerce giant, I can say, heavily relies on AI to personalize the shopping experience for its customers. They use again this machine learning, especially machine learning algorithms to analyze customers' browsing and purchasing history. Then again, making another thing is that making product recommendations tailored to individual preferences. And that approach actually contributed significantly to Amazon's success and customer satisfaction, even by I can say, reducing customer service response times by around 40%. So Amazon's actually data-driven product recommendation led to a 29% increase in average order value, as customers are more likely to add recommended items to their carts. Then personalized shopping, that result in more than 68% improvement in click-through rates on recommended products compared to other non-personalized suggestions. Then customer service, I already mentioned, shared that customer service response time have been reduced to 40% due to fewer inquiries related to product recommendations, because the customers find what they need more easily. Then personalized email campaigns driven by data science, they showed even 18%, more than 80%. This is only accurate percentage. So higher 18%, not approximate, not accurate, sorry, approximate percentage only I had mentioned in this slide. So higher open rate and again 22% higher conversion rate compared to generic email proportions. So no doubt in that, because nowadays we all are actually viewing that regarding this, the contribution of this particular organization, Amazon's, towards the field of AI. Again, Caterpillar, a construction and mining equipment manufacturer. This particular organization applies AI to support the agriculture industry. They use actually ML algorithms to analyze data from heavy machinery in the field and helping farmers identify maintenance needs. Then prevent costly breakdowns during critical seasons, and so on. So farmers who utilize Caterpillar's data science-based maintenance, they experience a 30% reduction in unexpected equipment downtime, ensuring that critical operations can proceed smoothly during peak farming season. Again, its predictive maintenance solution resulted in 15% decrease in overall maintenance cost. So I mentioned previously that because it helps farmers or prevent costly breakdowns, especially during critical season like that. Then again, by optimizing machinery maintenance schedules, farmers achieved more than 10% increase in operational efficiency that enables them to complete tasks more quickly and efficiently. Then again, one more point. Here actually I have mentioned only few points just to convince you all that the role or impact of this particular AI or machine learning towards this current organizations or contribution towards even industry also. So its data-driven approach actually contributed to a 20% improvement in the resale value of heavy machinery. Now another, Uber. Again, everyone, I think almost 100% in this particular audience is familiar with this Uber. What is the role of this particular Uber in AI and ML? Uber revolutionized the transportation industry by using AI. For what? To optimize ride sharing and delivery routes. So their algorithms actually consider real life traffic situations, driver availability, and passenger demand to provide efficient, cost-effective transportation services and so on. So Uber's driver specifically saying data-driven routing and matching algorithms led to an average 20% reduction in I already mentioned this, these are only approximate percentages. 20% reduction is travel time. Of course, more than 20%. Reduction in travel time for passengers, then ensuring quicker and more effective transportation. Again, by optimizing driver routes and minimizing detours, Uber has contributed 30% decrease in fuel consumption for drivers. That results in cost savings and reduced environmental impact. Again, it's Uber's real-time demand prediction models help reduce passenger wait times by 25%. That enhance customer satisfaction, then increase the number of rides booked, and so on. Then again, it enabled Uber, this approach enabled 100 million, even more than 100 million, I can say, active users to complete over 15 billion trips. 15 billion, it's not a number, more than 15 billion, I can say, demonstrating the scale and impact of their transported service. So anyway, so these are actually some of the case studies I mentioned, especially the
I think your video, that means the shared screens are not visible. Just try it.
PPT not visible?
Now, I don't know, it's my problem. I'm not able to.
Is the
It's
screen
visible, sir, to me.
Okay,
It's visible.
then it's okay. Okay.
Yeah, okay, thank you. Yeah. So, even though I had mentioned only few case studies, I began with IBM's healthcare. That is then Path AIs, again healthcare, then Uber services, one transportation I took, one healthcare, two, IBM's and Path AI. Then one agriculture I mentioned, Caterpillar, then Amazon, then Siemens. Anyway, I have chosen, then PayPal's finance, from the finance side. So actually, I have chosen these case studies from different fields. Not limited to these fields. Even though I mentioned only this finance or transportation, agriculture, healthcare, etc. But whatever be the field area which we are choosing, if the data is available, definitely we can come up with applying data science techniques or specifically machine learning algorithms, predictive techniques, so as to develop different AI tools. Simply, that's a conclusion, even because nowadays we can see that in healthcare, actually, one of the topmost position, this healthcare actually stands in the topmost position while dealing with this. They actually support our doctors strongly, especially to detect diseases or to diagnose using the patient from the patient records and so on. So even we can't say in one or two words the contribution of this particular term A and ML towards this world. Very rapidly changing across sectors. Yeah, moving, I think before moving the types of, I think now I can give a break, because now next I would like to share something specially on the types, or this using different types of role of types of ML towards each of this area. So, sir, can I
give
a
sure.
break now?
Yeah. All participants, thank you for your cooperation and a wonderful speech from Dr. Bindu Krishnan. So I think this is the time for 10 minutes break for all, and we will restart around 9:52.
7:30. Yeah.
Thank you.
Thank you. Shall we start or?
Yeah, ma'am. Yeah. So the first session is the first session already she explained the basics of the recent trends in the AI and machine learning techniques. And now I think she moved more deeper into that area and some applications in the second sessions. Hope you all like follow her talks, and please do marking the feedback of session 1 and also feedback session 2 that we will share later. So that is important, and also should follow these artificial intelligence and machine learning basics. Then from tomorrow onwards, we will going into the specific application. So this is, I guess this is the platform development for this FDP. Thank you all, and move over to you, ma'am.
Thank you, sir. Yeah. So first session, actually, I explained especially on what is happening, especially in industry, using this AI, or what are the applications. I have mentioned some case studies, especially in healthcare, different fields. But for all these things, actually, mainly, we begin with ML, no doubt in that. So I'm thinking of the second session, because one session is actually, in one way I can say, blah, 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 just like case studies, all those things. But of course, some participants expect something purely technically. So not fundamental things, but let me begin with some fundamental ML itself, and what all additions which we need to take care, especially while contributing towards the different fields, especially in healthcare. Because usually in academics, actually, even myself also, once upon a time, I was also doing like that. We focus only on, take the case of regression. We focus only on that accuracy. Yeah, okay, I got say 90% accuracy. Okay, it's a good model, or 90 above 90%, it's a good model. Let us continue with that. No. If we take the simple case of simply the case of regression algorithms only, don't focus simply on that particular accuracy only. Lot of other things are there. So I would like to share you, or just have a look on the additional things on some of the algorithms, some of the traditional. I'm focusing only on traditional algorithms. Because I'm not going in detail of those algorithms, because almost all the participants are aware of basic regression algorithms, linear regression or logistic regression or something like that. So let me start with, okay, let me share the screen. Yeah. So now I think no explanation is required. Let me begin with the say machine learning, of course. I think that is one of the A or ML. That is one of the term which I have used more in the last 1.5 hours. So it's rapidly changing the world, no doubt in that, from diverse type of applications and research, both in industry and academics. So actually, a lot of definitions are there. Machine learning is the field of study that gives the capability to learn without being explicitly, etc., etc., etc. I'm not focusing on the definitions of this. So anyway, one way actually ML or machine learning is concerned with the development of algorithms, computer algorithms, or simply algorithms and techniques that are able to learn. That is to improve automatically through experience. Machine learns from data, no doubt in that. So that is why we are defining it's a field of study that gives the devices or computers the capability to learn without being explicitly programmed. That means we are not going to teach the computer or device with a specific set of rules, but instead what we are going to do is we feed the device with enough data and give them time to learn by making its own mistakes and improve upon those. So usually we simply start with say, for example, an example of face recognition or pattern recognition. So every day we recognize our family members simply by looking at their faces or from their photographs, despite the differences in pose, lifestyle, or lighting, etc., hairstyle, or so on. Actually, we do it unconsciously and we are unable to explain our expertise, how we do it. So since we are not able to explain our expertise, we cannot write a computer program. At the same time, we know that a face image is not just a collection of pixels. It has structure, symmetric, there are eyes, nose, mouth, etc., located on certain place on the face. And each person's face is a pattern composed of combination of this. So what is the procedure happening there? By analyzing sample face images of a person, a learning program captures the pattern specific to that person and recognizes by checking for this pattern in a given image. So that is a procedure, example of pattern recognition. So I can say a simple example of it. So anyway, the goal of ML is to understand the structure of data and fit that data into models that can be easily understood and utilized by layman. Or automatically actually determine patterns. That is very, very, very important. Or use the uncovered patterns to predict future data. And again, of course, we know that we know that machine learning model. Usually what we do is that this machine learning means some training happens, then some models and testing happens, some performance measure, that's all. Yeah, that is there. I agree to that, a machine learning model. That can be a mathematical representation of a real world phenomena. Or to generate that, of course, we need to provide training data to ML algorithm to learn from. Then while training, of course, we pass an algorithm with the training data, and that learning algorithm finds patterns such that the input parameters correspond to output. Or actually that output of the training process, it's a machine learning model that we use for making predictions. Predictions can be, the models can be descriptive to describe something, or some predictive, or a combination of both. Or anyway, the ML is actually programming devices or computers to optimize a performance criteria using past data. Okay, so model means, of course, we have a model defined up to some parameters that can be descriptive to make, or predictive to make some predictions in the future, or descriptive to gain some knowledge from data. Sometimes that may be predictive and descriptive. So that is actually about ML. Now, one other thing is, what is the importance of mathematics as well as statistics? I can't skip that. Both are the statistics and machine learning actually closely related fields. One is a field of mathematics and another is a field of computer science. But what is the exact role? Machine learning uses the theory of statistics in building mathematical models. Why? Simply the core task is making inference from the sample. Simple reason. But the role of computer science is actually twofold. First one, in training, we need efficient algorithms to solve optimization problems, as well as to store and process the massive amount of data. That is the first one. Second thing is, once a model is learned, of course, its representation and algorithmic solution for inference needs to be efficient as well. So both plays major roles, especially for coding purpose, we approach computer science. Then for theoretical purpose, we approach mathematics as well as science. So anyway, coming to the types of machine learning, we know that there are 3 types or 4 types, both are correct. 3 types means that even we can skip this third one because this is simply a combination of supervised and unsupervised. So traditionally, of course, you might have seen only 3 types: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning, of course, the training data provided to the machines work as a supervisor. That teaches the machines to predict the outcome correctly, just like a functional form, y equals f(x) form. So it applies the same concept as a student learns as a supervision of a teacher. But supervised learning is again classified into 2, classification and regression. Classification happens when output is a category, but regression happens when output is a continuous number. Or regression techniques are used when the output is a real value based on some continuous variables. But in classification techniques, actually, we categorize data into some predefined classes. Different methods are there under this classification methods, such as logistic regression or naive-Bayes, etc. Then regression models, such as linear regression or logistic regression is a classification model. Then decision tree can be used for another thing, decision tree, which can be used for either classification or regression. Decision tree classifier there, decision tree regressor there. Then again, support vector machine, both classification and regression model, because support vector machine classifier there, support vector machine regressor there. Like that, so many other models are also there. But unsupervised means actually not training happens here. It's neither trained or neither classified or nor labeled. So a simple example actually, see, between what is the difference between supervised and unsupervised learning. So this is actually a case. See, machine learning actually just I'm going fast because I know almost all the teachers are aware of this machine learning. Just a quick refresh over. I'm not taking a machine learning class. Actually, I like to take, but since people are aware of this, just start with, say, 1 or 2 sentences on machine learning. But what I would like to share is that, especially while treating machine learning algorithm, what all additional things which we need to consider. Okay, so an example of, come back. Okay, so an example of supervised learning. This is actually a labeled data. So here actually this data is labeled as rectangle, circle, triangle, hexagon, etc. So we will pass this to the machine, then that will give you a model. Then after we will pass the test data, then it will predict whether it is a triangle or circle. So here actually we are focused with the labeled data. The same example, if we take this same example as a unsupervised learning, it will come like this. You will be given a set of unlabeled data. We are not aware of whether it is a triangle or rectangle, whatever the name, we don't know. Some unlabeled data. So what machine do is that we will pass this to the machine. So machine will classify these data into different group, where each group is having some similarity. Okay. Some similarity. So after that, if required, you can give some name for that. That's your choice. Okay. So machine will group this into different. Actually, we are using the term not group. We are using the term clusters. This procedure we call it as clustering. That is, group the unsorted information based on similarities or some patterns, etc. Okay. Definitely, each group is having some similarity. So here, it's very easy to understand by looking at this picture. So that is the difference between supervised and unsupervised. And in unsupervised also, we have one technique is this clustering. Other one is association, where one of the method or algorithm under association technique is a priori algorithm, where we are using simply the probability concept or conditional probability and market basket analysis. I think many of you are familiar with market basket analysis. Which is market basket, that is simply analyze the basket in a supermarket. So if we approach a supermarket, definitely we will, if we have a list of items, definitely we will start with a basket. We will collect item by items. Finally, we will come to the counter and we will pay the bill. Anyway, what is the need of analyzing this? So suppose we approached a supermarket for buying, say some rice dal, etc. And if you have a plan to buy, say, vegetables also, definitely if the supermarket is having the provision to get vegetables from there, definitely you will buy that vegetables from the same supermarket itself. So what is the need? So you have decided to buy some grocery items from the supermarket. Finally, you decided to buy vegetables also from the. So what is the probability of purchasing vegetable or selling the vegetable given that the other items already sold or other item already purchased? So here actually I consider or I shared you only the case of vegetables versus other items. Similarly, say for example, suppose you have a small kid or those having a small kid approach a supermarket for buying tin food like Cerelac, Nan or something like that. If the supermarket is having the provision to get, say for example, diapers, like Snaggy or Pampers, etc., definitely that parent, mother or father, will buy that item also from the same supermarket. Okay, provided that availability is there. So if we find the probability that diapers purchased, given or diapers purchased or sold, what is the probability of selling that diapers given the other item? So there we are using the concept of conditional probability. Even though we are using the term, big term, a priori, algorithm, association, etc., simple probability, conditional probability, probability of A given B. That means probability of an event A given that another event B already happened. Okay. So here actually in this particular example, I shared only the case of item to item correlation. Similarly, we can consider the case of person to person. Suppose a husband and wife visited a supermarket with the decision that husband need to purchase some shoe polish or shaving set or something like that. But while entering the supermarket, even though they have decided to visit the supermarket for buying only those shoe polish or some shaving set or something like that, if the supermarket is having the provision to get some ladies' beauty items, the wife will purchase from there, or some rice or some kitchen items or something like that. Definitely, that wife will be having the tendency to buy the kitchen items from there. So there, if we find the probability that those kitchen items will purchase, given that items chosen by that husband already purchased. So the need of analyzing these things, actually, definitely that supermarket owner can increase his profit in millions in the upcoming years. Because no, here I had mentioned only the case of few correlated items. How many items will be the correlated items will be there? Or how many individuals, persons visiting how many customers are there in supermarket per day? So if they analyze those data for the last 5 years or 10 years, definitely that corresponding authorities can increase their profits in millions. Okay. So for this purpose, what I want to share you here that for this particular analysis, actually we call it as market basket. Some technical terms are there, some small formulas are there, lift, support, etc., etc. Those who are familiar with this association technique. But anyway, the concept behind this particular thing is association technique, simply conditional probability. That's all. That is why previously I mentioned statistics or mathematics plays a major role in this machine learning models. Even people say machine learning, there is no machine learning without statistics or without computer science also, of course. Okay, so regarding this unsupervised learning, actually two types, clustering. One is clustering, which is a procedure for grouping a set of data objects into clusters. Or it's a class of techniques used to classify objects or cases into relatively homogeneous groups. And those groups we call it as clusters. And please note that objects in each cluster tend to be similar to each other and dissimilar to objects in the other clusters. That is, here, if we take objects from these groups, of course, these two things are similar, but is exactly dissimilar with the next groups. Okay. This particular thing also, this is also again clustering also used for market segmentation. Then case of this second one, association again, supermarket or supermarket chain where one application is market basket. That is finding association between products bought by the customers. If say, for example, if people who buy X typically buy Y, or if there is a customer who buys X and does not buy Y, or if she's a potential customer. So once we find such customers, we can target from cross-selling. So simple thing is that we are using only conditional probability for finding association. So then third case, semi-supervised, I already mentioned, it is simply a combination of unsupervised and supervised learning. Now, third case is reinforcement learning. Reinforcement learning, and here actually we have an agent and a reward with many hurdles in between. See, we have a robot here. Actually, this objective of this robot is to catch this diamond. Either he can travel through this way or this way or this way. Anyway, he has to find the best route with minimum time, minimum cost, etc., etc., etc. So the agent will decide what to do to perform the task. So especially in this reinforcement game playing is common example for this particular reinforcement learning, especially to predict the winner of chess, like that, something like that. We are using this particular reinforcement learning. Okay. Yeah, examples of machine learning. I think now everyone is familiar with the various only few examples I have mentioned here. Then again, automatic translation or image recognition, email spam filtering, text and speech, etc., 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 etc. Countless. So due to these examples itself, we can find applications of machine learning. Already, in the session 1, actually, I shared applications in various fields, including this medical diagnostic, finance, or marketing, agriculture, etc. Then, if we talk on machine learning algorithms, not I think now 100 plus algorithms. I think more 1,000 plus algorithms are there. 1,000 plus or 10,000 plus algorithms are there. But the traditional algorithms, of course, includes our linear regression, logistic regression. Here I focus only the traditional algorithms. Linear regression, logistic regression, decision tree, support vector machine. Then K-means clustering, then KNN, K-nearest neighbor, principal component analysis, etc., etc. So let me start with the linear regression. Please don't think that even though this particular algorithm is emerging, we are actually heard about this algorithm only for the past few years, but it's not like that. This particular linear regression, I'm not adding the word algorithm. Linear regression is more than a century-old method in the field of statistics for fitting a line or a plane to a real value data. From the machine learning perspective, of course, we look at it as a system of learning weights in response to examples from the domain. Anyway, because even though it's more than old century method, that time actually statisticians are having the limitation to deal with large volumes of data. When it comes to machine learning, then only it actually proves its capability, I can say. Anyway, so from the machine learning terms, we can say that it is based on supervised learning, but it's a statistical method to model the relationship between dependent and independent variable, or target variable and predictor variables. Simple example, say only two variables I have included here. So if we want to predict the salary of a particular person based on a number of years, what we do is that we will fit a regression model. Simple, since we have only two variables, one variable, whatever be the variable which we are going to predict, that we call it as dependent variable or target variable. Whatever be the variable which we are going to predict, that variable we call it as dependent or target variable. The variables that are used for prediction, we call it as independent or predictor variables. So here, if you are going for prediction of salary, then here salary is the dependent variable, and we are using this independent variable for prediction. So this is the independent variable. Okay. No, so since we have only one independent variable here, for this particular example, it is enough to proceed with simple linear regression where the line, simple line which we all studied in our school classes, y equals mx plus c, or y equals ax plus b, or y equals beta 1x plus beta naught plus beta 1x is the simple linear regression, provided we have only one dependent and one independent variable. Similarly, if we have more than one independent variable, then we move to multiple, where only one dependent variable there. So in case of more than one independent variable, we move to multiple linear regression, where here y is the dependent variable, x1, x2, x3, etc., xn is the independent, are the independent variables. Okay. And of course, if we fit a model like this, definitely our objective is to find beta naught, beta 1, beta 2, etc. Because once we get the values of these beta naught, beta 1, etc., it is possible to predict future value for y based on this x1, x2, etc. So for that, actually, for estimating beta naught, beta 1, of course, from I think in machine learning, we usually proceed with least square method, but a lot of methods are there. MLE method, other methods, other moment methods, etc., etc., etc. Anyway, let me focus on the method of least squares. So there, what we do is that we will find the since this equation is not exact, of course, some error term involved there. We will. I'm not going into the revision to all those things. Anyway, we need to minimize this expression. By minimizing this is actually sum of squares of error. So by minimizing, or simply by minimizing, means we are using the concept of in calculus, first derivative equal to 0, second derivative greater than 0. So we are actually differentiating this particular term with respect to each of those constants, beta naught, beta 1, then equated to 0. By simplifying that, we get the values of all these things. Actually, we are doing in Python or whatever be the programming language, using the coding. Python, actually, even we are not actually directly using this particular expression. We are simply by importing that sklearn, simply give a code linear regression. That's all. But the things behind this particular word linear regression is that how do we get this expression? Since this relation, actually, we are assuming this relation. We are not sure whether this is correct. So what we do is that we will add an error term, say plus e, y equals beta naught plus beta 1x plus e, some error. So that e equals y minus beta naught minus beta 1x. That is the thing which we have substituted here. So minimizing this expression. So actually that principle of method of least square, even though we are using method of that method itself says that the best values of these constants are those for which sum of squares of error, that is this term, is minimum. So that is why we are using. Anyway, that is the method of getting beta naught. So after getting this beta naught, beta 1 expression, excuse me, 1 second. One second. Yeah, sorry. Okay. So let me share the screen once again. Okay. So, yeah. So after getting these values of beta naught, beta 1, etc., what we do is that from the machine learning perspective, initially we find this using training data set, so that we will get a model. We will use another data set for testing. Then we will find some, say, mean square error or maximum of R square value. That's all. So what happens if we simply stick on to, because if the R square value is near to 1, definitely we will proceed with that model for future predictions. Now I am saying that please don't stop with that simply R square value or mean square. Of course, our aim is to minimize. In general, I can say optimize the cost function or loss function. In this case of regression, optimize means minimum. Our aim is to minimize mean square error. That is correct. I agree to that point. But of course, simply looking at the, we can improve that, this particular thing. Of course, these constants, we can improve the constant by updating weights or by using gradient algorithm. All those things are there. But what I suggest or what I recommend is that after finding the mean square, so what is the mean square error? Before that, what is mean square? Say, let us have a look at this particular example. Effect of temperature and reaction. Just 3 columns. Simply, I have included 3 columns: time, temperature, yield. From this data, of course, it is possible to predict time based on temperature and yield. It is possible to predict temperature based on time and yield. And of course, it is possible to predict yield based on time and temperature. Assume that we are going to predict yield. So that problem or objective I am giving you is develop a model for yield in terms of time and temperature. Okay. So if we are going to predict the yield using linear regression, we can assume the model as yield or expected yield equals y equals beta naught plus beta 1 x1 plus beta 2 x2, or yield equals beta naught plus beta 1 into time plus beta 2 into temperature. Simple thing. Then by method of least squares, we can find beta naught, beta 1, beta 2. Okay. And assume that you are getting this beta naught as yield equals beta naught is this value, beta 1 is this value, beta 2 is this value. Here minus, I am getting beta 2 as minus. That is why plus into minus is minus. Or anyway, fine. Okay. So after getting this model, what we do is that, so this is our data set: time, temperature, yield. This is actually actual value of it. Same as this one. It's same as in the previous table. Same thing. I am repeating here. Serial number, time, temperature, yield. That is the original data. So this is the actual yield. So let us take the first row value of time and temperature. Time equals 130, temperature equals 190 in this particular equation. You will, by solving this equation, you will get a value of yield. That value is this one, 36.2185. Predicted value of yield. Then substitute each row values of time and temperature in this particular obtained model, so that you will get a set of yield values. That is this column. Okay, predicted yield. And of course, logically, this is the actual yield. This is the predicted value of yield. Difference between these two values is error. Error, or another term for that, residuals. See, 35 minus 36.2185 is this thing, 81.7 minus 76. This is actually our errors. Error corresponding to each row in our data set. Okay. Now, this column is a combination of positive and negative values. So what we do is that we will take the square of error, square of this last column. Again, after taking the square also, we have to find a representative value. That is why we are finding the average of those squares. Just combine it. We are taking the square of error, then find the average. Take the reverse. Average of square of error. That is same as our mean square error, which is one of the performance measure in linear regression. I hope all of you are evaluating this one, mean square error. Average of square of error. Fine. But just I am asking you one thing. Since it is a square, definitely minimum value is 0. So our objective is to attain this mean square as error as small as possible. But just I am asking you one question. Suppose you are getting the mean square error as 5,000. Do you conclude that the model is good or bad? Good, or do you conclude that the model is bad? Some people are taking this concept like, oh, I am getting this model mean square as 5,000. It is too large. Oh, my model is not good. Anyway, I don't know. Some people are taking the reverse. Oh, since my data set is very large, there is nothing wrong in continuing with this particular mean square as 5,000. It's good. See, by looking at the mean square error, whether it is high or low, we are not actually able to reach a unanimous decision that our model is good or. Of course, there are ways to improve that using the gradient descent, etc., etc. Simply, I would like to share you that simply looking at the mean square error, we are not in a position to reach the conclusion that our model is the best one. That is one thing. Okay, now move to the second thing. Okay, by simply leaving that mean square error, let's move to the R square value. Accuracy. Regression in R, actually we are getting, I don't know, all of you are especially those who are doing the machine learning project. There actually in Python, if you are doing in Python, we use the term dot score. That code is dot score. Simply we get a accuracy. People are saying like that, but because I found many people claiming that similar to the accuracy in classification model, some percentage there. Here also you are obtaining a percentage, but that percentage or accuracy in linear regression, we call it as R square value. Even I always say the term accuracy, it's not a correct usage in regression. In regression, don't use the term accuracy, use the term R square value. In classification, of course, we can use the term accuracy, but in regression, it is not a correct word. It's R square value, which always lies between 0 and 1, or it's a percentage. Say if it is 0.8 means 80% accuracy, I agree to that. But what is R square value? It gives us a degree. That is how much that dependent variable is influenced by the independent variable. Especially the variation, how much variation is there in dependent variable, that can be explained by the independent variable. So for that measurement, actually, a degree, even one formula itself, one mathematical expression itself there for, but those who are aware of ANOVA, analysis of variance, only they will get that idea, because the expression for finding R square value is 1 minus ratio of residual sum of squares and total sum of squares. Okay, this residual sum of squares means error sum of squares. All those things actually come from this ANOVA. This regression and analysis of variance, it's closely related. So anyway, so R square value, I agree to the point, it is equivalent to the accuracy in classification, but try to use the word R square value itself. That thing which we are using in Python, that thing which we are doing with the code dot score. Okay. Now, another thing is that people will usually focus, people in the sense researchers, especially from computer science side, or those who are doing machine learning project, usually stick on to maximum of these two things. I don't know, even I can find at least one person or one participant from this group who focus on more evaluation techniques, especially while doing the regression, linear regression. I don't know. Anyway, if you are doing it, it's good. Of course, I appreciate that. Anyway, moving to that. Okay, so while doing regression techniques, in addition to this R square, adjusted R square, of course, we are focusing on, especially if we have, in the case of multiple variables, we focus on just an adjustment to R square, but that we take, especially in the case of multiple linear regression. Root mean square, that is not that much necessary. But anyway, what I want to share is that in addition to these, certain other things. One thing is, How many of us are checking the assumptions of linearity or assumptions of regression before moving to applying a regression procedure? So that is the difference between especially some techniques used in statistics. Of course, I know that limitations are there in statistics actually, or in mathematics. Computing power, that limitation is there. But some theoretical concepts are there. I recommend even, especially those who are doing projects, machine learning projects and data science projects from the computer science also, please check these assumptions also before moving to regression. One is linearity. Of course, we know, because even linear concept, linear regression, that word itself clear. Independence of errors. What is that? We have to check the independence of these particular values. Different ways are there. Either you can plot a graph, or different methods are there for checking this independence of these observations. That is one of the assumption of linear regression. See, our objective is to make our model as accurate as possible, as best as possible. So for that, we have to check as much goodness criteria if we are able to check that much good or that much better. Okay, so assumption, second one is independence of error. Then third one, normality of errors. What is that normality of errors, or equality of variances of random? Normality of errors. See, these are the errors, or we call it as residuals, right? It is possible to check whether I'm not saying that it is possible. It is, I recommend, it is mandatory to check the normality of these particular errors. How do we check the normality? Simply by drawing a graph, but in most of the cases, simply by drawing a graph, you may not be able to say whether it shows normal or not, or it shows normal distribution or not. So that is why we can approach some other techniques, such as some tests are there, statistical tests are there for checking normality. Shapiro test, Ryan-Joyner test, Anderson-Darling, or Coleman, etc., etc., etc. Usually this Shapiro test, that is very easy. In a single line code, we can do it either in R or Python or any, whatever be the software. So for these tests, actually, we assume the null hypothesis that data follows normal. Then the conclusion, how do we make the conclusion? Simply in your output, look at the p-value. If the p-value is less than 0.05, we reject the null hypothesis. That's all. Those who are familiar with testing of hypothesis, they might be able to catch this very easily. Those who are not familiar with the testing of hypothesis, maybe it's difficult to understand this. So these are the tests. See, those who are not familiar with the testing of hypothesis, there are some visualization techniques for checking normality. You can approach that. PP plot, probability plot, or QQ plot, quantiles plot, quantiles plot. So interpretation is very simple. Just make a PP plot using a single line code. If our points lie in this straight line, that means your data follows normal, or that errors follows normal. If it lies in this straight line. If these points lie away from the straight line, data does not follow normal distribution. Okay. Then again, methods are there. See, here actually I am taking the plot of residuals versus independent variables. One plot is residuals versus independent variable, or residuals versus predicted independent variables or predicted variables. Okay. So from the residuals means error, our error, last column, error. So if we make a plot like this, the interpretation is that there should not be any pattern for this particular plot. There should not be any pattern. Okay, so that again shows. So I just want to say, actually in linear regression, even though you are familiar with only these some R square value, mean square error, there is a section in regression residual analysis. So I recommend to just go through that, and where some of the things which I mentioned actually comes under this residual analysis, or we can use another word, model diagnostic, regression model diagnostics. Okay, so I recommend to read that and apply those things also, especially while doing regression techniques. Here, even though I mentioned regression techniques only, similar cases are there if we approach the other machine learning techniques such as logistic regression or decision tree or support vector machine, etc., etc., etc. Okay. Yeah. In between, just if participants having some queries, even you can clear it now itself. Don't wait for during the end of the session.
From chat box, ma'am, I noticed 2 questions to you. One
Okay,
is,
let me check.
I just tried it. Can you please let us know about any 1 or 2 techniques used by PayPal? That's first question. And second is, what are the various data-driven machine learning models used these days? These questions arise during your session.
Sir, do I need to check from the beginning? Yeah.
Only these 2 questions I
Can you please let us know about 1 or 2 techniques used by PayPal? Yeah, PayPal actually use this particular regression. Regression itself actually they are using. Linear regression technique, especially while dealing with quantitative data, they are actually using regression techniques. Even other techniques such as decision tree, I'll come to that. Then decision tree also can be used for in case of quantitative, or if it's a categorical variable, in that case also we can use decision tree. Even logistic regression, naive Bayes, all those things we can use, especially in case of categorical data. So specifically, they are using machine learning algorithms, traditional machine learning algorithms, and of course, neural network techniques also. Then what are the various data-driven machine learning models used these days? Of course, we begin with linear regression. I think almost these 2 questions are same. First one is by PayPal. See, machine learning models, actually traditional machine learning models means we begin with linear regression, then logistic regression, then decision tree. If it's a continuous variable, simply numerical data, that's all. We begin with linear regression, linear regression, simple linear or multiple linear, I explained. But here actually, I have given just a refresh of the machine learning algorithm with the thought that people are aware of basic machine learning ideas, because almost all participants are from computer science background, and I focus more on especially that performance metrics, because from my side also, once upon a time, especially while beginning with the machine learning projects, I have focused only on that accuracy. People say accuracy, that I suggest try to avoid that word, especially in regression models. So linear regression, actually we are using the term R-square value. Okay. So there is an expression, I can show you if required, what is the expression for, but it's closely related to another technique, analysis of variance in statistics. 1 minus residual. I can show you that on machine learning PPT there. Then second case is we are able to apply this linear regression only if the variables output or output or target variable, dependent variable is continuous, numerical value, quantitative data. In other cases, so if you want to predict whether it is yes or no, if you want to predict whether it is pass or fail, in those cases, we approach logistic regression or a naive Bayes classifier or some classification models. But decision tree, support vector machine, K-nearest neighbor, these 3 can be used either as a classifier or regressor. But again, suppose, see, we are provided with a data set, a large volume of data set, and if we want to segregate or sort those data set into different groups with some similarity, first we need to approach clustering technique. Okay. First, we need to approach clustering technique, which is an unsupervised algorithm. Then we can, simple example I can say, suppose we want to teach a child, a small kid, say a different fruits. If we are provided with the images of different fruits, fruits of vegetable, sorry, fruits of apple, orange, banana, etc., 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 say some 1,000 images. Initially, it would be good to sort those images into different groups, such as apple, images of apple as one group, images of orange as one group, images of banana as one group, etc. So that procedure, we call it as clustering. We can use the clustering technique for that. So after sorting that, we can pick each group and you can teach that child the images of apple, then images of orange, like that. So that predictions is some technique, but there actually apple, orange images, all those things are categories. We are using some classification models in supervised learning in the second stage. Okay. Then I think only 2 questions are. Ma'am, regression is also based on error calculations. Not based on error calculations. After getting the regression models, of course, we have to find the performance of the model, right? So for finding the performance of the model, we have various performance metrics, where one of the performance metrics is mean square error. If the value of mean square error is less, then our model is good. Okay. So for finding mean square error, find the error. How do we find the error? Actual value there, find the predicted value, difference between those actual and predicted. That is the error. Okay. So, but that error actually, it's a combination of negative and positive. So we have to normalize it. So that is why we are taking the square of those values. Even while taking the square of those values, we have to find a representative value. That is why we are finding the average. So average of square of error, that is same as mean square. Okay, so it is an error, right? Representative of error. So always logically thinking, when the error becomes minimum, model becomes good. So our aim is to minimize that mean square error. Between MLE means maximal likelihood. Yeah, see, here actually, I had mentioned in between, there are various methods for finding coefficients. That is beta naught, beta 1, etc. Coefficients of regression model. One is method of least square. Okay, we are differentiating, etc. Another method is MLE, maximum likelihood estimation. Maximum likelihood estimation, actually, we are approaching in a different way. First, we need, there actually, we couldn't skip the concept of probability distribution. So we assume that a set of samples comes from a probability distribution. So there actually, that especially that normality concept is very, very, very important. Because we assume that these samples or our data set follow some normal distribution. Then find the PDF. Some mathematical things are there. Find the PDF of probability. PDF means probability density function of each of these samples. Say f of x1, f of x2, etc., etc. Find the product of those. After getting the product, we call it that product as likelihood function. Those who have some stats background, they will pick up this very easily. Hey, not stats background, I think computer science people, they are also familiar with the maximum likelihood estimation. Just brush up that. Okay. So find the product of PDF, that we call it as likelihood function. Okay. Then differentiate that, like those actually that this particular method says that those values that maximizes the likelihood function, those values of beta naught, beta 1, beta 2, etc. or constants which maximizes the likelihood function. So there actually we are taking the case of max. That is why in general we call it as actually optimize the cost function or loss function. In case of MLE, actually include function. There we are taking the maximize. But if we are treating mean square error, we are looking into minimize. Optimize means maximum or minimum. Okay. So between MLE and minimizing, I think you got it. Normality is same as normalization. Normality is same. Normality means actually we are checking the condition that the data follows bell-shaped or not. Normalization means actually we have the provision to convert our data set to normalize or standardize. Normalize, say by taking, I think some of you are familiar, by taking the difference between mean divided by standard deviation. So if X is the value, X minus mean average divided by standard deviation. That is a procedure for converting given data. But here I am not telling you that convert the data set into normal. Here actually one of the condition which we need to check is that this particular data follows normality, especially the errors. Okay. After getting the residuals or errors, check those errors for normality. Different ways are there for, I am not asking to convert.
Okay, ma'am, I have one small question.
Yeah, please, please, sir. Please.
So normality check, is there any number is like it's a cutoff, any number, the number
No.
should be this one or minimum number of samples?
Any value
to...
from minus infinity to plus infinity.
No, I'm asking about the sample set. For normality check, we use the samples. So is there any kind of limit like
limitation to the data set number of no, sir, nothing.
Okay.
Nothing.
Okay. So how
Only
to
thing is
select
that
Shapiro with this test for a particular application? What is the basis of selecting the Shapiro Wilks test for the...
No, not only Shapiro, that is the simplest one.
Okay.
Okay,
Very
that's all.
simple.
You can use any of the test. Even I have showed in the PPT only 4 tests. I'm not saying that there are only 4 sets.
Okay.
Both of normality tests are available.
Okay. Got it. Thank you.
Okay. The only thing is that with a single line code, especially I think sir also from computer science, right? Right, sir?
No, I'm just...
Anyway, those from other than stats and maths. Okay, it is enough to, especially other than, just I want to ask you that if you are a mathematics or statistics person, I can explain it more easily. That is why. Especially non-mathematics or non-stats people, it is enough to look at, easiest method, enough to look at the p-value. P-value less than 0.05, 5% means significance level. P-value means actually it is the smallest level of significance in which hypothesis is rejected. So if it is less than 0.05 means data does not follow normal. Sorry, does not follow normal in the sense, if the p-value less than 0.05 means we reject the null hypothesis.
Yeah, got it.
Reject means reject the null hypothesis that data follows normal. So finally we conclude means just opposite. Okay, so we do normalization first, then check. No. Don't do normalization for the error. See, normalization, doing normalization means we are actually converting the data set to each value minus its average divided by standard deviation. But in the case of a regression, we have to check whether our data follows normal or not. That is one of the methods for checking our performance measure. If it is not normal, I am not saying that your model is good. Right? Your model fails good accuracy, best accuracy. Okay. Don't go for what is the need of normalizing that error. Here, actually, there is no need of normalizing the error. Even you can have it with your data set. There is nothing wrong in that. But I'm not sure even you normalize it, you need to get the error as normal or not. That may not be sure. Especially while applying some basic statistical tests such as t-test, f-test, etc., data needs to be normal. So in that case, you can normalize it. But here actually regression concept is entirely different. Here actually one of the condition for getting best accurate model is your data or errors follows normality. Kirti, hope you got the idea. Okay. Okay. Anyway, now again, can I move to continue the session?
Yes, ma'am. Yes.
Okay. Okay. I'm actually, especially while sharing, just I'm closing the video. Otherwise, no, especially during that introductory session, no, that time I face some network issue. Is it okay, sir?
Yeah. No issue.
Oh, okay. Yeah. Yeah. One more thing I would like to share. Yeah. So this is the one which I was showing. Yeah. So I had talked about this. This figure is these figures in between. I skipped nothing. See, these are our original actual data point, and this is the fitted one. That's all. Actual values of actual values of that yield, and this is the regression fitted one. I think we all are familiar with that. Then this is nothing. Those who forgot the basic concept of y equals mx plus m is the slope and c is the intercept. We all studied in the in our school classes, but just to remind you that, see, this is the intercept. Okay, beta naught. And slope is beta 1 is actually y equals beta naught plus beta 1x or mx plus c. C is this thing, intercept, and m is the slope. Slope means difference between y coordinates, y2 minus y1 divided by difference between x coordinates, x2 minus x1. Okay. Again, yeah, this is the case of R square value, that is degree to which variance independent. This is same as the accuracy which you all used in regression. So of course it lies between 0 and 1. If it's near to 1, it indicates perfect fit, otherwise poor fit. Then, yeah, this is simply, yeah, this is the expression which I would like to show you. See, expression for R square value. 1 minus RSS means residual sum of squares divided by TSS means total sum of squares. Residual sum of squares is same as error sum of squares. And again, the expression for residual sum of squares is, or error sum of squares is, see, I have just noted this. Don't worry about the expression. I will explain that. Sigma, sum. Difference between our actual, see, sigma of E square, same thing. We are actually finding the square of something, right? Square of error, same thing. Error sum of squares. See, find the difference between actual and fitted. Actual minus predicted. Whole square. Take the sum of all values. That's all. Just not taking the average, that is only difference. Okay. Now, what is this total sum of squares? Total sum of squares is actually sigma of y. Y means actual value minus mean of those values. Actual value minus mean whole square. This particular thing actually, it is closely related to analysis of variance or ANOVA in statistics. That is why one of the reason, the next parameter or next performance metrics which I am going to, now I explained only two things you are already aware of that is R square value and mean square error. I think almost on machine learning projects we can see that. Then I suggest you to check for those assumptions, normality concept, or that plot of, where is that? This, at least one of the test among these. But if you are not aware of testing of hypothesis, you can approach some probability plot or QQ plot. PP plot or QQ plot. Then you can check this plot, that is just make a plot on errors versus independent variables, that is residuals along y-axis or errors along y-axis, independent variable along x-axis, and errors along y-axis, predicted variables along with that. But please keep in mind, there should not be any pattern. If there is some straight line structure or curvy linear structure or something like that for this particular graph, that means your model is not good. Okay, we are not ending with this. I can share you two more tips. See, after obtaining this model, where is that? I think just a minute. Yeah. Okay. Now, next, again. So in addition to this normality or this plot or R square value, or mean square, etc., next thing I would like to share with that. See, after getting the model, find the summary of the model. Okay? Not this one. Just a minute. Look at this. Find the summary of the model. Yeah, okay, this one. Find the summary. That is, check whether your model, that is obtained model, this particular model is overall. Just a minute. Just a minute. Yeah. Yeah. Okay. See, after obtaining this model, we have this model means this one, y equals yield equal this one. Okay. In addition to this R square, mean square, etc. Again, we have to check the overall significance of this model. How do we check the overall significance of this model? Actually, the things which we have found out is this value, then this value, then this value. But we are not sure whether these values are good or not. Okay, so two things we can check regarding the significance. One is we can check the overall significance of this model by simply giving a code summary, something like that. Okay. For that, we use another test, or in statistics, we call it as F test. Say, for example, by getting the summary, you will get a table like this. So here it is to check the overall performance of your obtained model. Simply don't be confused with all these things. It is enough to check this p-value. In some softwares, this title of p-value will be probability. That is only different. Especially in R, you can see that here it will be written as probability. But in Python, p-value, you will get it as p-value. P-value, or actually p-value, it's a probability. Okay. So find or look at the probability or p-value corresponding to F distribution. That is very important. Okay. So all these things you will get it simply by giving a single line code summary. That's all. Okay, now how do we conclude whether our overall significance is good or not? If this p-value is less than 0.05, why I am using this 0.05? In almost all softwares, default value is 5%. Okay, but you have the freedom to change it to 1% or 10% like that according to your convenience. Default is 5%, almost all softwares. So here, if the p-value is less than 0.05, then we conclude that our overall model in the sense y equals this obtained overall model is this one. This one, this model, overall model is significant. That is one thing. But we are not stopping with that. I'm not stopping with that. Again, even though your model is overall significant, it is not necessary that individual coefficients are significant. Okay. Even though you are here, actually, I got p-value as 0.00, which is clearly less than 0.05. So I am concluding that my model is overall significant. Regression model is overall significant. But even overall model is significant, it is not necessary that my model is significant over different variables. So that is why after checking the overall significance, we have to check the significance of individual coefficients or individual variables. For that, we use t-test. See, you will, even by taking the summary itself, you will get this table also. In addition to this table, in addition to this particular table with p-value but please note that for checking overall significance, we are using F-test, F distribution test or F-test. But for checking individual significance, we are using t-test. That is the difference. Now, how do we check that? See, intercept, don't look at the intercept because intercept is actually required always. See, here actually my variables are time and temperature. I have used time and temperature for prediction of yield. So my variables are time and temperature. Corresponding to this time, look at the p-value or probability value. This heading will be p-value or probability. That will be different in different softwares. So corresponding to this time, that is here p-value is 0.05, which is clearly less than 0.05. So I can conclude that time is good for prediction of yield. Once again, corresponding to each of, we have to check each of these variables corresponding p-value we need to check. So corresponding to time, here I have the p-value 0.0. That means less than 0.05. So I can conclude that the variable time is good for prediction of yield. But look at the p-value corresponding to temperature 0.7, which is greater than 0.05. That means temperature is not good for prediction of yield. Okay, in that case, we have to, what we do? We have to, actually our obtained model is this one, right? See, our obtained model is time based on, yield, model for yield based on time and temperature. I check the overall R-square value I am getting as a 0.8, mean square value also very less, normality, everything check. I check the overall significance, that is also good to proceed. But only thing is that finally I am getting temperature is not significance of, while checking significance of temperature, it is not good for prediction of yield. So in that case, what we will do, we have to develop a new model without temperature. That is the procedure which we not adopt. Because now our aim is to get that model accuracy as good as possible. I know that we know that, oh, then deleting, see, this is a simple example. I showed you only three variables. You will be dealing with more number of variables. See, so say if you are dealing with 10 variables or 12 variables or 1000 variables or something like that, ignoring 1 or 2 variables, that is not a matter of fact. Provided if you focus on getting best accurate model. But be frank, industry, in most of the cases, this is not possible. Thing is that industry is purely client oriented. Client will not allow us to remove this variable. In that case, we have to proceed with the time itself. But anyway, for getting that, just I'm sharing you that for getting the accurate model, definitely check the significance. If some value is less than greater than 0.05, it is not significant. In that case, you have to remove those variables and we have to develop a model for yield based on time only. So definitely in that case, in this particular example, we will approach simple linear regression. That is y equals yield equals. Then in that case, intercept also will be different. because we are going to proceed developing a model without temperature. So we are actually deleting this particular column, and we are considering only time and yield. So definitely yield equals some intercept, not this value, some intercept plus something into time. After getting that model, you need to check it again. All these things, R square value, mean square error, then normality test, or that plot of error versus individuals, or error versus that independent variables, and error versus dependent variable, then the overall significance. Because now we are here in this particular example remaining only one variable, but in your case actually, even though if you remove one or two variables, you will be having more variables again. Okay, so repeat this procedure. So that is about regression, and again I am telling you that these are not the only things for checking this regression. Some other model diagnostic tests are there, say for example multicollinearity. I don't know how many of you are familiar with the multicollinearity test. That is actually multicollinearity means, see, we are actually calling, in this particular example, we are calling time and temperature as independent variables, right? Independent variables. How can we assure that those variables are independent? We are actually assuming that they are independent. So before moving to fitting the model, check the multicollinearity and confirm that they are independent. Several methods are there for checking that. So anyway, if we go in depth of all these things there, right? One area itself is there, regression model diagnostics. Okay. So which even one book also I can suggest, Introduction to Linear Regression by Montgomery and two other authors, M-O-N-T Montgomery. I think I can share in the chat. Linear regression by linear regression, or introduction to linear regression analysis by Montgomery. Okay, during the end of the session, it's a personal copy with me, so I'll show you by opening the video. Montgomery and two other authors. I don't know spelling is correct or not. Anyway, okay. So that is good. That's a good one. Some simple mathematical things are there, but not in detailed derivation. That focus on especially some case studies are there. So especially those people from other background, I mean non-maths or non-stats background, they are able to understand very easily while reading that. So it's good thing. Many case studies are there, especially focus on this. Some mathematical things are also there, but not that much. Okay. So anyway, that is a case of regression. Now, I think time is there. Going to okay. Up to 9:30, sir. Okay, I think up to 9:30. Okay.
Yes, ma'am.
Yeah. Okay. Yeah. Then logistic regressions. I will move to not and I'm not finishing. Yeah. Now moving to the second technique, which is a classification model, not a regression model. That means classification models can be used for prediction of categories or classes. So if you want to predict whether it is apple or orange, or if you want to predict it is yes or no, of course, more than two categories we are handling. But anyway, this is also an old statistical method, logistic regression. So it's a statistical technique to find the probability of dependent variable, but in supervised learning, again, it is a supervised learning to use to predict the probability of it. So here, why that, even though this is a classification model, why the name logistic? People are confused. Oh, logistic regression means it is a regression model. No. It is a classification model. Then why this name came for logistic regression? This particular thing has a close relationship with linear regression. But here we are using the concept of odds ratio. In probability, there is a concept of odds ratio. What do you mean by odds ratio? Say, for example, if we have two things, probability of boys, probability of girls, then odds ratio means ratio of probability of girls divided by 1 minus. Okay, probability of girls. That is odds ratio. So here actually we are using the concept of odds ratio. That is x by 1 minus x, odds probability. Okay, take the logarithm of that. Maybe those who are familiar with logistic regression, people familiar with logistic, only you might be aware of only this expression. Sigmoid function. Of course, we are using this concept, but how do we get this expression? Sigmoid function 1 divided by 1 plus e power minus z. Or this is same as if you take e power minus z outside. If we take that term in the numerator, we can express the same thing in this way also. This we call it a sigmoid function. See, actually, this expression, sigmoid function expression for sigmoid function is obtained from this particular term, where x, number of girls or probability of girls, divided by 1 minus of that. X by 1 minus. This actually we call it as odds probability, odds ratio. Take the logarithm of that. Logarithm of odds. Okay. So if we take f of x, or say, for example, z equals log x by 1 minus x. Okay. Cross multiply it after taking exponential. E power z equals e power log x by 1 minus x, or e power z equals x by 1 minus. E power log x is x itself. So x by 1 minus x, cross multiplying, simplifying, you will get, find an expression for x. Find an expression for x, which is same as this one. So that is this inverse function, that's all. Okay, just inverse function of this particular log odds. Okay, this we call this actually logic transformation. Okay, so anyway, come to the sigmoid function. So in logistic regression, simply we are using this expression for prediction of our category. For example, if we substitute any value for z, 1 by 1 plus e power minus any value from minus infinity to plus infinity, you will get after simplifying this, you will get a value lies between 0 and 1. So that is why the graph of sigmoid actually ranges from 0 to 1. See, look at the x values, any values. Y values means this function values lies between 0 and 1. And usually we put a cutoff here. Here I am putting a cutoff, say 0.5. That is, for example, if our probability value lies above 0.5, that is lies between 0.5 and 1, we can conclude that our outcome is, say, pass. If it lies below 0.5 means 0 to 0.5, between 0 and 0.5, we can conclude that the outcome is fail. Okay, so or we can make a cutoff value other than 0.5. So anyway, there should be a threshold value. Okay, so here the predictions are based on probability. Now, what is the relation between this logistic regression and linear regression? Why that term regression comes in this particular logistic regression? See, in this sigmoid expression, this Z is same as our linear regression model. That is y equals that beta naught plus beta. That is 1 by 1 plus e power minus of beta naught plus beta 1 x1 plus beta 2 x2. But anyway, if you substitute those expression here, minus of beta naught plus beta 1 x1 plus etc. But if you simplify this whole expression, definitely you will get a value lies between 0 and 1. But if you look at that y equals beta naught is y or z, beta naught plus beta 1 x1 plus etc., you will not get a value lies between 0 and 1. If you substitute here and simplifying 1 by 1 plus e power minus z, you will get a value lies between 0 and 1. So that is the relation between linear regression and logistic regression. In logistic regression expression, sigmoid function, we are using linear regression. Okay. But anyway, The basic difference is this thing, and in linear regression, we are getting a straight line. In logistic regression, the curve is in this form, etc., etc. Here it is not linear. Here actually prediction is based on probability. There actually prediction is value itself. Some continuous value lies between minus infinity and plus infinity, like that. Okay. Yeah, this is a one simple example. That is, you have to predict when a car will break down. Okay, based on number of years since last service. You are provided with a data set. Two variables are there. Number of years since last service, and here this is the probability. You are given a data set with a number. You have to decide when a car will break down. Okay, see, look at this number of years since last service, first year, second year, third year, etc., etc., etc. So here, suppose this is the threshold. Okay, this is the threshold, 0.5. So here, from corresponding to this threshold, see, look at this. This line actually crosses here. Corresponding to this point, I have a number of years of service, something around 3.5. Okay, between 3 and 4, around 3.5. So we can say that the threshold value 0.5 indicates that the car is more likely to break down after this particular point. Okay, after 3.5 years, this point, 3.5 years of usage. See below, look at this, below this point, probability less than 0.5, the car will not break down. Because number of years below this. But above this point, see, look at this point, car, probability greater than 0.5, rounded to say 1, greater than 0.5, car will break down. Okay, that's one simple example. Okay, so here anyway, prediction is based on probability, not based on a value. And it is not necessary that always you will be given only two options, because there are various types of regressions, multinomial, etc., etc., etc. So more than two cases also, say I can show you different types. Yeah, binomial regression, actually, if we have only two classes, we approach binomial regression. Say pass or fail, yes or no, like that. But if you have more than two classes, we approach usually multinomial regression. Only thing is that, especially while doing programming, it is enough to give this word multinomial, that's all. Okay, orderly means if your data is some orderly data. Say for example, rating 0, 1, 2, 3, 4, 5, like that. Okay, 5 means high rating, 0 poor rating. In that case, you can approach this ordinal regression. So this is actually mathematical side. I have already explained this. This is actually regression. So that sigmoid function, that is same as this Z. Z is same as Ax plus B. Or if you have more than one variable, beta naught plus beta 1 x1 plus beta 2 x2, etc. Okay. This is one simple example. Yeah. Anyway, in classification models, actually, performance measures, it is not like in the case of linear regression or regression models. Here we are using these accuracy. Usually people look into only this first one, accuracy, that is percentage. How do we get this accuracy? All these things actually are based on a matrix known as confusion matrix. Some of you are familiar with this. True positive, false positive. What is this? True positive. Suppose in your actual data set, you have the option pass corresponding to the first column, first row. Okay. In the actual data set, if you have the option pass in the first row, and assume that one more thing here, positive negative means if you have the classes as pass and fail, you can read pass as positive, fail as negative, or you can read fail as positive and pass as negative. It's your choice. Suppose assume that you are treating this positive cases as pass, negative cases as fail, or positive cases as on, negative cases as off, or positive cases as high, negative cases as low, something like that. Okay, let us stick on to say positive cases as the category high, negative cases as the category low. Okay, just to avoid confusion, that is why I have ordered that pass fail. Okay, so positive, assume that the positive cases as high, negative cases as low. Okay. True positive means if the actual data you will be given as high and your predicted also high. Predicted case. See, I showed you that case of linear regression. You will be given a set of actual data. After obtaining the model, it's your duty to predict predict each row, output of each row corresponding to your model. So while predicting the output of each row corresponding to each row, suppose the actual output is actual output is high, your predicted also high. Okay. Count the number of those options. Actual high, predicted high. So actual positive, predicted also positive. Count the number of those high, right line. That number is the true positive. Number of true positive. Okay, simply predicted value matches with the actual value. Actual value positive, predicted model. Predicted also positive. Then take the case of true negative. Actual negative. Negative means low. Predicted also negative. So those columns, those rows with low. Count the number of those rows. That is the true negative. Predicted matches the actual value. Actual value negative means here we are assuming negative as low. Predicted also low. Then you can imagine what is false positive, false negative. False positive. Positive means high. Okay. So actually is high. False positive means you are wrongly predicted. If you will get the predicted as low. So those column with actual as high and predicted as low. Count the number of those possible cases. That is false. False positive. Similarly, false negative. Negative. What is negative? Here we are assuming low as negative. Okay. False negative means just wrongly predicted. Wrongly predicted means prediction will be high. So those rows with actual as low, predicted as high. Count the number of those rows. That is false negative. So anyway, count, find the number of true positive, number of false positive, number of false negative, etc. Then it is very easy to find all these things are actually based on simply this confusion matrix. See, for example, accuracy. Accuracy is obtained by sum of true positive and true negative. See, just imagine what is the definition of probability? Number of favorable cases by total number of cases. Favorable cases, definitely we are treating the case of true only, right? True high, true low. Take the sum of those favorable cases divided by total number of cases. So this is same as actually all of us are finding, yeah, I am getting accuracy as 90%, 99%, etc. They are actually while doing coding, simply by doing a single line code, dot score, you will get this thing. But anyway, in classification models, we are using this same term itself, accuracy itself. But in regression, R square value. Okay. Similarly, another performance measure is regression, is precision, especially if you want to check whether our model is reliable or not. So precision is obtained by, and also especially precision recall, all those things are having more importance if we treat with more than 2 classes. Okay, in the case of two, then you can ask me another question. In the case of more than 2 classes, how do we find true positive, true negative, etc.? In more, see, this table is actually the case of only 2 classes, yes or no, on or off, pass or fail. If we have 3 classes, it will be a 3 by 3 matrix. If we have 4 classes, it will be a 4 by 4 matrix. Take the case of 3 classes.
Hi, ma'am. Sorry to interrupt you.
Yeah, please, sir. Please, sir.
The time is up.
Oh, sorry. Okay. Let me wind up. Okay, so these are this is the case of 3 classes. So here true positive, all these things. See, for example, true positive cell 1, whatever be the value here. This is actually true positive corresponding to first class. True positive corresponding to second class, third class, etc. So since the time is anyway over, just I am stopping the session. quickly. If you have any doubt, you can ask me.
Participants, if you have any questions related to session 1 and 2, please.
Second session is actually purely technical.
Yeah.
First session, just I have given an overview of recent trends in AI and ML. Especially, I focused on from the industry perspective.
Okay. No questions means I would like to thank Dr. Bindu Krishna for her valuable words related to artificial intelligence, especially the basic things like why we learn the probability or statistics for doing the machine learning. So those kind of basic things, basic explanation related to machine learning, it's truly a game changer for like people like computer scientists or computer science people, computer teachers, etc. So I hope all the participants should they also received some insight from these discussions, and thank you all. Thank you, Bindu ma'am, for this valuable things. And once again, I would like to thank all the participants, and they are participated like something like they are through the meeting chat, they participated it's exceptionally. So good night to all, and tomorrow's session will start around 6:30 p.m. and there are 2 different sessions tomorrow. So all are please join tomorrow around 6:30. So good night all, see you soon. Thank you. Thank you.
Thank you. Thank you. Thank you all. Thank you, sir.